There we are. All right. Please take it away, Tim.
Okay, thank you very much, Pete. Let me thank the organisers for inviting me to present at BQIT. It was a little sad that we can't all be in Bristol ourselves, but it's certainly great that the opportunity to still give this presentation is here. So I'm going to talk about noiseless amplifiers and CV quantum repeaters and some new protocols that we've come up with recently, which I hope you find interesting. The basic motivation here is to find ways to mitigate the effects of loss on quantum channels. Loss affects different quantum optical encodings of quantum information in different ways. But something I think is quite interesting is that CV, or continuous variable approaches to error correction, are agnostic about what encoding you're using. And so this sort of motivates us to look at these sorts of approaches. So I'll start by reminding you about noiseless linear amplification, and then tell you about our new protocol, and then go on to talk about CV quantum repeaters. So noiseless linear amplifiers are able to amplify coherent states without amplifying their quantum noise. Deterministically, this would be impossible, but probabilistically, one can do it, and it's useful because you can herald the successful events. The best way to think about how these amplifiers work is in terms of their number state, their Fock state coefficients, which get amplified by this g to the n value. But because of this, there must be an energy constraint on the alphabet that can be faithfully amplified because g to the n is unbounded. And in general, it turns out that the larger your energy constraint, the smaller the value of the probability of success. The interest in, one major reason for interest in noiseless amplification is its ability to distill two-mode squeeze states, or EPR states. So if you put an amplifier on one arm of an EPR state, you increase the entanglement. More importantly, if that EPR state has traveled through some loss, then putting a noiseless amplifier on it can both increase the entanglement and increase the effective transmission. So how do you do this in the lab? The first demonstration was by Jeff Pride's group using a modified quantum scissor. And what that enables is to correctly amplify the 0 and 1 component of your state, but then truncates all components above that. A different approach was demonstrated by Marco Bellini. So here, again, the 0 and 1 components are amplified correctly. The higher components are amplified a bit, but not by this value you would expect. So in our first paper about this, we proposed this setup for getting beyond just the 0 and 1 case. Here we put several quantum scissors in parallel coherently. And what happens there is, suppose you put 2 in parallel, then you do get this g squared on your 2-photon Fock component, but you get this unwanted factor of a half. As you go to more scissors in parallel, then you get more components, and slowly these coefficients stop, go towards what you want, which is 1. As you make it larger and larger, the probability of success drops dramatically. Ideally, what you would like is to be able to do this. Just faithfully amplify all the Fox states up to some particular cutoff. But up until now, the only way known to do that was via a highly nonlinear interaction, and so not practical. As a result, all of this experimental demonstrations up to this point have worked in the very low photon number regime, except for this last one here, but that's because that's actually noise-reduced amplification rather than noiseless amplification. So the question is, can we do this sort of ideal transformation, but in a experimentally practical way? And I hope you will have guessed that the answer is yes. This is the one scissor. So this, we inject a 1 photon state and we count 1 photon at the output, and we get this truncation at 1 photon, but it's faithfully amplified up to that point. So our new protocol is what we're calling a 3 scissor. The form of it is very similar, except now we inject a 3 photon state as our resource, and we count 3 photons out of the 4 output modes here. And what that does is this ideal transformation. All the Fock components are faithfully amplified up to the 3 photon component. And you notice it's all linear optics, so it's much more practical. So how well does it work? So we can compare it to the putting scissors in parallel, and we see that the fidelity is improved over 1, 2, 3, or 4 scissors in parallel. And at the same time, the probability of success is better than the 4 single quantum scissor protocol. So it works better and at a good probability of success. So another way to evaluate how well this works is to look at this distillation protocol. So we're going to consider an EPR state where one arm has gone through some loss, and then we're going to noiselessly amplify it and compare what happens with the 1 scissor and the 3 scissor. So for the parameters chosen here, we see that the 1 scissor saturates because of the truncation and can't reach the deterministic bound. So the deterministic bound is the maximum amount of entanglement you can push through this lossy channel by basically starting with infinite entanglement. On the other hand, we see that the 3 scissor can go across this bound. What's more, if we consider these dotted lines, they show a realistic case where we have assumed that the detectors have 70% efficiency and the input state, the resource state, also has only 70% efficiency. Of course, you take a hit in the probability of success, but it's still not sort of beyond the realm of practicality. Okay, so that's it for the NLA, for the 3 scissor anyway. So now let's change gears and look at quantum repeaters. So we've seen that one way to mitigate loss is to use an NLA. And for example, if we send an EPR or a 2-mode squeeze state through the loss, then that will improve it. But of course, this is probabilistic. So we can turn this into a deterministic protocol by preparing offline the entanglement through the NLA. And when it succeeds, then teleporting our desired state through the channel. And if the parameters are chosen correctly, then we can get an improved channel. And basically any state can be teleported through here. So then if we want to go to longer distances, we can concatenate this error correction protocol. So one way of doing this is to put 2 of them in series, 2 of these in series, and then treat that as the loss in here and concatenate the entire thing in an overall error correction protocol. In that way, we can keep the effective loss static whilst increasing the actual loss. And this can be concatenated further. This was a protocol that Josephine Diaz and myself put forward 3 years ago, but we wanted to try and find a better way of doing this, and that's what I want to tell you about now. So here's our little error correction protocol again. So we're going to look at a different way of concatenating this. We're going to just mirror image it. So this now becomes an entanglement swapping protocol, but we're going to use, the entanglement swapping protocol of Olscher, Obermeyer, and Peter van Luke, which unlike CV teleportation, you send classical channel information in both directions. This turns out to be the optimal thing to do. Now, there have been other CV quantum repeater papers that have used entanglement swapping, but they'd used non-Gaussian entanglement swapping, and so non-deterministic. Here, this is deterministic with linear optics. We can also consider an asymmetric version of this entanglement swapping protocol by swapping around where the two-mode squeezing and the quantum scissor lies. So quite amazingly, just at this level, this device works as a quantum repeater. So the way quantum repeaters are usually defined is in terms of the secret key rates you can achieve in QKD. It's not the only way to do it, but this is one way that's been popular. And basically we can see that our device, both the symmetric and asymmetric device, are able to cross these bounds. So direct transmission means basically the same protocol, but just without the repeater, without the link, whilst the plob bound is the best you can do with any protocol. The protocol we're using here is the no switching CV QKD protocol. So what about concatenating this further? So this turns out to be quite simple. You can just basically mirror image again the whole setup to get a 4-link protocol shown here, and you can just keep doing that. So by going to 4 links, we were able to cross the direct transmission bound at a shorter distance. By going to 8 links, we get over the plob bound at a greater distance. We can see with 16 links, we can get right out to 1,600 kilometers with a reasonable sort of key rate. So we think these are pretty exciting results, and you know, looking forward to further developments. So I should say these rates are significantly better than previous CV repeaters, and I just want to emphasize here that this is with just one central station, so just 2 links. We can already see repeater-like behavior. I also showed you this new NLA, so I should just point out that the NLA used in getting these results is just a single quantum scissor, and we're currently looking at what happens if we use this 3 scissor in such protocols. Okay, so I'm basically at the end now, so I just want to show you a picture of the people involved. Matt Winnell is my PhD student at the University of Queensland. Neda Hosinendaj is my postdoc at the University of Queensland. And Josephine Diaz is now at the National Institute of Informatics in Tokyo. And so that's it from me, and I'll just stop there and say thanks.
All right. Thank you, Tim. I'll clap for I think there's over 250 people in the channel. So thanks very much for that. We're ahead of schedule. I'm
a little quicker than I thought.
I'm just looking for any questions here. So I've got one on the Slido channel from Anonymous. What impact on imperfections on detectors, e.g. dark counts, or not projecting on exactly on Fox state 1, like bucket detector? So it's a question about imperfections and dark counts.
Yep. So this is, are we talking about, so if we're talking about the 3 scissor, then basically this realistic curve is not changed by going to a bucket detector. We haven't looked at dark counts, so I can't really say what would happen there. The 1 scissor is reasonably, at low gains, is reasonably resilient to dark counts, but but like I say, I can't really say for the 3 scissor. In terms of the effects of that in the repeater protocol, we haven't looked at what happens in the repeater protocol with inefficiencies and stuff like that for this new protocol. In the earlier protocol, it could withstand small amounts of loss. So we would expect something similar to happen in this protocol.
Okay, thank you. Here's another question from our own Josh Silverstone. Are there any NLA applications in metrology?
Okay, that's an interesting question. I mean, there have been suggestions of applications in metrology, but there have also been refutations. So I think if you're basically just looking for an increase in signal to noise in some situation where you can repeatedly probe the signal, then it won't help, because the probability of success will just reduce your effective signal greater than what you would have suffered without the NLA to start with. However, if your metrology protocol can somehow use some sort of, well, okay. So in a situation where maybe the signal is changing in time and you only get 1 shot at it, then you might be lucky and get a good shot if you use the NLA. Another possibility is preparing offline resources that you can then use in some metrology protocol, and being able to prepare those offline resources better by using the NLA. Like if you needed entanglement in your metrology protocol, there might be ways of using the NLA to improve that entanglement.
Okay. I'm just going through the list of questions here. I think, I guess the questions that get uploaded the most are the ones I should ask next. So there's one from Maria Chekova. What is an NLA physically? And then it asks, is it a phase-sensitive parametric amplifier?
No, physically it's well. So the one of the ones that has been demonstrated experimentally is shown here. So we just physically, it's 2 beam splitters. So this is a single photon input state as a resource. You tune the gain using this eta here, which is the beam splitter ratio, and the state you're amplifying comes in here. So if we're only using, so this setup has been demonstrated several times experimentally. So our new protocol is very similar. We have the beam splitter. We now inject a 3-photon Fox state as our resource state. The state to be amplified comes in here. Then we have this little interferometer here. And what is required is that 3 out of these 4 detectors clicks with a single photon.
Okay. We've still got 5 minutes in the session left, so if you're all right, Tim, I'll ask another question here, quite popular. This is from Alex Clark. He says, Alex says, great talk. In the 3-scissor, what happens if the 3-photon state is imperfect, i.e. a 2-photon state enters instead? Does post-selection remove these?
Okay, so this is an interesting question. So I should point out that in this graph, we are allowing for the 3-photon state to suffer loss. So sometimes only 2 photons will go in, sometimes only 1 photon, etc. And so you can see that it's, so there's basically a 70% beam splitter in front of this 3-photon state for the dotted lines there. You see that it still works pretty well. In fact, if you only put 2 photons in and you still count 3 photons at the output, then as far as coherent states are concerned, then it faithfully does basically a 2-scissor. It amplifies it, the 0, 1, and 2 states faithfully. But that's a special case that only applies to coherent states. For other states, it gives a phase flip on one of the outputs, which is not, in certain situations, isn't too detrimental, but is not an ideal case. So, I mean, one reason I think that that this generalization hasn't been found previously is that you can't do it exactly for 2-photon truncation. And so people, obviously, after the 1-scissor, they thought, well, let's try the 2-scissor, and it basically didn't work. But it turns out that the 3-scissor does work. The next one, quite strangely, after the 3-scissor that works, is the 7-scissor.
Okay, we've got time for one more question here. Well, I'm going to mention 2 that are, well, maybe not. I thought they were both somewhat foundationally related, but the one question is: 3-scissors look like interaction-free measurement setups. Is there a relationship? And there was also something I wanted to tack on. There was another question that was, does the NLA have impact on loopholes for non-locality tests?
Okay, I'll take the second one first because the answer's reasonably easy there. That's yes. Mm-hmm. And you can find a discussion of that in papers from Jassan's group from about 5 years ago. The first question, actually, there is a direct relationship with another protocol, this 3-scissor, but that's the tele-amplification protocol that has its history goes back to the cat computing papers of the early 2000s, but it was demonstrated by the group of Sasaki. And basically, if you take a cat amplifier where there is a 4-lobed cat sitting here and the input states are superpositions of 4 different coherent states, and then you reduce the amplitude of the cat, then for an odd cat, it ends up reducing to a 3-photon Fox state. and turns into an NLA.
Great. Okay. That's bang on our 25 minutes. So many thanks again to you, Tim, and to the people who asked questions in the audience.